We're now going to study the unit circle. The unit circle is extremely important. If you understand the unit circle, you can find almost any trig identity that you will ever need to know without having to memorize it. A unit circle is a circle whose radius is 1 and its center is placed at the origin of an xy coordinate system, with the x-axis lying along the horizontal and the y-axis lying along the vertical. You can see a unit circle shown on the screen. Inside the unit circle is inscribed a very special triangle as shown on your screen. It is a triangle whose hypotenuse is 1 unit in length and starts at the origin and extends to a point on the circle that can be represented by an x and y coordinate. The angle theta is drawn counterclockwise from the x-axis to the hypotenuse. Using this special triangle drawn inside the unit circle, it is possible to derive many important relationships about trigonometry functions. These relationships are called trigonometric identities and can be very useful in solving physics problems. There are far too many trigonometric identities to memorize all of them. Instead, we will find almost any identity that we need if we understand the unit circle and can do algebra. For those few trigonometric identities that occur often in physics problems, you will eventually find that you will memorize them, and that this will save you much time. The first thing we see is that the adjacent side of the triangle lies along the x-axis. So we have the x-coordinate of our point on the unit circle can be found by finding the adjacent side of our triangle. This says that x is equal to our hypotenuse, which is 1 times the cosine of theta, or simply the cosine of theta is the same thing as the x-coordinate on our circle. The opposite side of the triangle lies along the y-axis. So we have that the y-coordinate on our circle point is given by the opposite side of our triangle, which we can find with our sine function. Y equal the hypotenuse 1 times the sine of theta, or for this special triangle, simply sine theta. It is important that I put a note of caution here. X is not always equal to the cosine of theta. It is only equal to that for the unit circle. The same thing is true about y being related to the sine of theta. Students often feel that in any problem on any type of triangle that they can do this. This is yes for the unit circle. In physics problems, you will have a beam, for instance, that is measured and becomes the hypotenuse of your triangle, and maybe it's 10 meters. But the angle will not be measured in the way that it was measured for the unit circle. If you apply the idea that x always is found by finding the cosine and y components are found by using sine, you're about 50% of the time you will get the problem wrong. Use the way I taught you earlier for finding sides of a triangle. If you want to derive trigonometric identities using the unit circle, then when you draw the unit circle like I've done and draw the triangle like I've just done, you can use the fact that the x-coordinate on the circle is the same thing as the cosine theta of the triangle, and the y-coordinate on the circle is the same thing as the sine of theta, and this is very powerful. We will now use our knowledge of the unit circle and triangles to help find some basic sines, cosines, and tangents that we will need to check our work. There are certain angles that you should learn their sines, cosines, and tangents. These are the angle 0, 30 degrees, or pi over 6 in radians, 45 degrees, which is pi over 4 in radians, 60 degrees, which is pi over 3 in radians, and 90 degrees, which is pi over 2 in radians. You need to know these off your head because they show up a lot, but also because it enables you to estimate the answers that you're punching on your calculator for other angles that you do not know. So these group of angles, I will expect you to know the sines and cosines and to be able to give them to me whenever I ask for them. Starting with the angle of 90 degrees, we'll use our knowledge of the unit circle. Here I have the radius and the hypotenuse of my triangle pointing straight up along the y-axis. Its coordinates are 0 along the x, 1 along the y. That means that the cosine of 90 is 0, the x-coordinate, and the sine is 1. The tangent is found by 1 divided by 0, which is equal to infinity. For 0 degrees of an angle, the hypotenuse lies horizontally. In this case, the x-coordinate is 1 and the y-coordinate is 0. So we have cosine of 0 is 1, sine of 0 is 0, and 0 divided by 1 gives us 0 for the tangent function. For 30, 45, and 60, I'll show you later that the cosine of 30 is the square root of 3 over 2, the sine is 1/2, and the tangent is 1 over the square root of 3, or the square root of 3 over 3 if you prefer. For 45 degrees, the sine and cosine are both the square root of 2 over 2, and the tangent is 1. At 60 degrees, the cosine is 1/2, the sine is the square root of 3 over 2, and the tangent is equal to the square root of 3. You should memorize all of these. Let's now look at a couple other examples. The first is a 45-45-90 triangle. For the 45 degree angle, the opposite and adjacent sides I know from geometry class have to be the same size. I also know that they're a square root of 2 smaller than is the hypotenuse, but I'm not going to use that in this particular thing. I'll show you how without that I can still find the sine and cosine. I also have a 30-60-90 triangle, and I happen to know that the smaller side across from the 30 degree angle is half the length of the hypotenuse for that. This is something I also remember from geometry. I will now use my knowledge of the unit circle to find the sine and cosines for these two particular angles, 45 and 30. Starting with the Pythagorean theorem for my 45 degree angle triangle, I have a squared plus the second side, which is a squared, is the hypotenuse squared, which is 1. Combining terms, I have 2a squared is equal to 1. A squared is equal, therefore, to 1/2. Or a is equal to the square root of 1/2, or if you prefer, the square root of 2 over 2. But the cosine of 45 degrees is equal to a, the adjacent side, and the sine of 45 degrees is equal to a, which is the opposite side. So I've just proved that the sine of 45 degrees is equal to the cosine of 45 degrees, and they're both equal to the square root of 2 over 2, as I had in my table. For the 30-60-90 triangle, I have, by the Pythagorean theorem, 1 squared is 1/2 squared plus a squared. Moving and isolating a squared by itself, I have 1 is equal to 1/4 is a squared. This gives me 3/4 is equal to a squared. Taking the square root of both sides, I get a is the square root of 3 divided by 2. So the cosine of 30 degrees gives me the square root of 3 over 2, which is a, the adjacent side. And looking from the triangle, the sine of 30 degrees is the opposite side, which is 1/2. This gives me both values from my table as well. What if I wanted to find the sine of 27 degrees or of 68 degrees and I was a person in ancient Greece and I didn't have calculators to do this for me? Well, I could still do what we just did. I could draw a circle to scale on a piece of paper. I could draw the triangle or not draw the triangle and measure a point for a given line at a given angle. That's my hypotenuse. And then by measuring the x and y coordinates on the paper with a ruler, I could have found the values of cosine and sine. This is how people built the ancient buildings long ago when they didn't have calculators and they didn't have computers. Today, if you want to know the sine of, for instance, 70 degrees, what I know is it's greater than the square root of 3 over 2. So it's going to be greater than, for instance, about 0.83. Maybe it's 0.88. And I know it's less than 1. So if you know the basic angles, then you can get an approximation and check your work on a calculator. And we use calculators rather than using graphical techniques. But it is possible to find them all with a ruler. You just can't find them really to 7 decimal places like we do modern work. As one more example of finding things using the unit circle, I'm going to show you how to find an identity. Here I've drawn my triangle as usual with my theta there and my hypotenuse of 1. But I've drawn a second triangle connecting it over here where the hypotenuse is again 1, but I have a new angle, an angle alpha, which is 90 degrees, the entire right angle, minus this angle theta. So alpha is 90 minus theta. This can give me some identities. For instance, this side here in green is found as the cosine of theta, the adjacent side to theta. It is the same length in this square as this side here, which is the opposite side found using the sine function for alpha. So sine of alpha, which is the sine of 90 minus theta, which is this side, has to equal the green side here, which is the cosine of theta. This is a trig identity. Another identity is the opposite side here, which is found using the sine of theta, is the same length as this side, which is the adjacent side to alpha. So cosine 90 minus theta has to equal sine of theta. Another useful identity is this distance, x, and this distance, y, gives us a unit circle formula of x squared plus y squared equals the radius squared. In this case, 1 squared is 1. But we also can say, since this is cosine and this is sine, that instead of x we have cosine squared theta, plus instead of y we could say sine squared theta, and that's equal to 1. Another extremely useful identity. This is an identity that you will want to memorize, as it is used all the time. There are many more identities that you can get. All you have to do is play with the unit circle.